Okay, everybody is very welcome to join the webinar by Max Lipton, MIT, and his title is Pseudodifferential Methods and the Mobius Energy. Max, tell us about this.
Yes. Okay, so thank you very much, everyone, for coming to join me today, and thank you for the organizers for inviting me to give this talk. So I'm going to talk a bit about pseudo-differential methods and the Mobius energy. And where I personally am at with this project is I'm still trying to catch up on all the prior work that has been done, and it's involved many different methods from many different fields. In prior talks, I've spoken about Freedman, Wang's original paper showing the existence of minimizers for the Mobius energy. That paper involved several topological methods. It's a very beautiful paper. I highly recommend you read it. But today I'm going to talk about a paper by Zhangshu He, published a few years later, that strengthens the original result, that shows that the minimizers are not only do they exist, not only are they C1, C11, but they are in fact smooth. All derivatives exist. And the methods involved in that paper are quite significantly different than what was originally shown in Freedman Wang's original 1994 paper. I should also just make a quick mention that in the paper that this talk is based off of, a lot of it was actually conducted when Zhangshu He was at CMAT back in around 2000 or so. So with that said, let's just get into the preliminaries. So let gamma be a rectifiable curve in Rn. Usually the most interesting cases are 3. Typically, we can also apply the definition for the Mobius energy on intervals, so we can look at the Mobius energy of curved segments. But for here, we're going to assume that everything is defined from the circle to Rn, precisely because we're going to apply Fourier methods, and thus this allows us to take advantage of Fourier series. So given such a curve, and we're only assuming it's rectifiable so that we can actually make sense of the integral, whether or not it's finite or not. The Mobius energy is defined as the double integral over the domain S1 cross S1. It should say that in the limit there, of the inverse of the pairwise distances squared. That is the extrinsic distance in Rn. And then we subtract the pairwise intrinsic distances inverse squared. So that is distance along the curve. And then we integrate with respect to the arc length parameter, because we want our Mobius energy to be invariant under reparametrization. So in other words, we want the Mobius energy to be a property of the image of the curve, the geometry of the object, rather than the functions that we happen to use to describe it. Okay, and so some of the basic properties, clearly for simple closed curves, the Mobius energy should be finite. So in other words, when the curve self-intersects, the energy blows up. That's because when we have points with large intrinsic but small extrinsic distance, there's no cancellation in the integrand, and so we have a Euclidean singularity of the order 1 over norm squared, and so that would force the integral to diverge. so one of the remarkable results from Freedman and Wang's original paper, which in this talk I'm not going to go into too much detail about, is that the Mobius energy is in fact invariant under the so-called Mobius transformations. So one can see that this energy is invariant under standard Euclidean similarities, so scalings, rotations, translations, reflections, etc. But under spherical inversions, we also have invariance under the Mobius energy. And just as a quick remark, it's not obvious to, it's obviously not obvious to see why the Mobius energy is invariant under Mobius transformations, but at least for the first term involving the extrinsic distance, taking into account the arc length parameters, we have that that term is just the product of side ratios for two triangles, and those are preserved under Mobius transformations. So at least for the first term, we can see that there's some invariance. The second term involving the intrinsic distance, which is, of course, highly nonlinear, that's going to that takes some hard analysis to show invariance of. And again, I'm not going to go into detail on how precisely that was shown. And also, one of the big results was that if we have a prime knot type, so that is, we have a knot type in R3 that is not the connect sum of two other non-trivial knots, we have that there exists a parameterization of said knot type, which minimizes the Mobius energy. And so that's very desirable because we want because this gives us, in some sense, a canonical representation of a knot. And there are many different ways to think of how a knot parameterization can be canonical, such as, you know, smallest curvature with respect to having a fixed arc length. But even though we don't know the explicit parameterizations for these minimizers of the Mobius energy outside of the trivial unknot case, in which case it's a circle. This the existence of these minimizers is something that's inherently interesting. And I should also mention that because of the fact that the energy blows up when it's self-intersecting, when we run the gradient flow of the Mobius energy, we can at least be guaranteed that we won't have self-intersections during the gradient flow, because that would cause the energy to blow up. So at least with that regard, the knot type would not change when undergoing a gradient descent. However, other types of singularities can occur for non-composite knot types, namely, because of the scaling invariance of the Mobius energy, you can have non-trivially knotted segments of your curve essentially shrink down so much so that it ceases to exist in the limit, and the Mobius energy would not be able to detect that. And so that's where that's part of the reason why having prime knots is important for the existence of minimizers. Here's just an example of a numerically simulated parameterization of a Mobius minimizer for the trefoil knot. One should also mention that, of course, by Mobius invariance, I can apply any set of Euclidean similarities along with spherical inversions of this curve to get an equivalent Mobius energy minimizer. But there's no like explicit example, but you can kind of see some of the geometric properties that arise when you at least try to numerically solve for one of these Mobius minimizers. So like notice that there's this kind of tightening phenomenon in the center where we have points that are intrinsically far apart but are extrinsically close together, and that's kind of serving as a barrier preventing the knot from self-intersecting and thus decrease or changing its knot type to something that is similar. to something that is simpler. Okay, and so the main point of Freedman Wang's paper was that the critical points are C11. That is, they are continuously differentiable and they have a bounded derivative. So that was in the original 1994 paper. A few years later, which is what I'm mainly going to be talking about today, Shangshu He of the original research group showed that the critical points are in fact C infinity, so all the derivatives exist. So that paper had a couple of technical ambiguities that needed to be resolved and were eventually resolved by a writer in 2009, and namely it involved issues regarding integral truncation in some of the integrals involved, as the Mobius energy involves integrating over a singularity. It's a singular integral. You have to think about how you truncate the integral in order to take a limit and show that the way in which you truncate it is does not affect the value of the functional. And also one would also have to show that that continuity of these functionals is preserved under reparametrization of the curve, because a lot of these processes to find the gradient descent, for instance, involve just continuously reparametrizing our curve in order to maintain a fixed total arc length, and so it's not entirely obvious that when we apply those reparametrizations, we still maintain continuity of the energy functionals. But in fact, that's something that's something that is indeed showed in Ryder's paper. And then in 2018, which is a few years ago, or maybe slightly longer than a few years ago, Blatt and Vorderobermeyer, they showed that not only are the critical points smooth, but they are analytic. So that is, not only do the derivatives exist, but the Taylor approximation locally converges, or I guess in this case globally converges, when you have a simple closed curve because the domain is compact. And so, to my knowledge and their knowledge, that was the first analyticity result for a non-local partial differential equation. Okay, so to talk about the Fourier methods that he uses, I have to take a little bit of a detour and talk about equivariance, which is going to be the theme of today. Equivariance is a very categorical topic. Obviously, this work is quite far from the traditional category theory involving commutative diagrams, etc. But the principle, I believe, is one of the main inspirations behind where a lot of work on just like general equivariance comes from, namely equivariance in the context of the Fourier transform. So if G, and I'm using ambiguous terminology intentionally here because a lot of these definitions can be interchanged and it's not clear what the specific objects, how to classify them are. But suppose we have that G acts on two sets X and Y, and suppose between X and Y we have a transformation of some sort, hopefully some form of some isomorphism or some bijection or whatever. Equivariance means that the actions and the transformations commute. So that is, this commutative diagram indeed commutes. So we can either act upon our object and then transform, or we can transform and then act upon our object. So in this specific context, G is the polynomial ring, which is a subset of the space of smooth functions. And our spaces that are being acted upon, x and y, they're going to be the same, and it's going to just be some PDE solution space. So it could either be, in the most general sense, it could be distributional derivatives, it could be some LP space, and T is going to be the Fourier transform. So more specifically, there are two different actions on function spaces based on polynomials. We can either multiply a polynomial with a given function to get another function, or we can, assuming we have a notion of derivatives, which in this case we will, we can take, we can view our polynomial as a linear differential operator and then apply that to our function. So we have these two different actions. And also just recall we can have the Fourier transform where given a function, we can convolve it with the exponential e to the minus 2 pi I x dot c, or its inverse transform. And so, in other words, we get these two functions that switch variable names from x to c, and in more complicated settings, we can have kind of a mixed Fourier transform where we have functions that are based on both x's and x's, and our polynomial ring has coefficients in functions of the variable xi. And so then we have just the general space of pseudo-differential operators, which are represented by just general smooth functions of the x and c variables, and see how both of those actions apply to our function space. And of course, the integral defining the Fourier transform is not absolutely convergent on general functions in LP or L2 or whatever, but of course we start with the space of functions of compact support. Then we can extend to the Schwartz functions, which are the functions that have that are rapidly decreasing even when multiplying by a polynomial. And then we can take approximations in general L2 to extract an unambiguous definition of the Fourier transform. And so we can still write an integral even if we're not technically integrating a function or even something that's in some LP, because you can also define the Fourier transform on distributions. So one of the most well-known relations of the Fourier transform is if we multiply the transform by a monomial in the xi variable, the frequency variable, where alpha is some multi-index, then that's the equivalent of first taking the corresponding derivative before transforming and then transforming. So in other words, this relates the action of multiplying by a monomial and taking a derivative. So this is the equivariance relation I was looking at earlier. And of course, the 2 pi I factor, that's mostly a conventional choice that I'm using. Some authors choose to divide the definition of the Fourier transform by 1 over 2 pi or 1 over 2 pi I or something. Ultimately, the important thing is that you just remain consistent. So again, we have this well-known relation that expresses the equivariance of these two polynomial actions on function spaces. And so this means that when classical derivatives don't exist, we can instead transform to the frequency side, and then we can multiply a polynomial and then transform back, and we can recover what the derivative at least should have been. And so you can just verify this method works in the classical space of smooth functions with compact supports, where all derivatives and integrals unambiguously exist, verify this formula holds, and then you can use that formalism to expand just ever so slightly to extend your notion of taking a derivative. So this is one way in which you can recover weak notions of a derivative. And so in particular, in a Sobolev space, which is a subspace of L2, of some LP, particularly in L2 where the Fourier transform goes from L2 to itself unitarily, this allows you to to have an expression of the weak distributional derivative of said function in LP in L2, assuming it exists. And when our polynomial p, not the p exponent, but the polynomial p, has non-integer degree, well, on the frequency side, it still makes sense to multiply by a function that doesn't have integer power, integer degree. And then when we transform back, assuming all of our operations are well defined in some sense, then we can extract a new notion of fractional calculus. So we can take the half derivative. So in other words, that means we take the Fourier transform, multiply by c to the power of 1/2, and then transform back. If that is something that is, if that process is well defined at each step, then we can say that we have invented the derivative of order 1/2 or any other non-integer. And in particular, on the frequency side, because by the Stone-Weierstrass theorem, we have denseness of polynomials in the space of smooth functions with compact support, with respect to convergence on compact sets, then you can approximate these non-integer degree functions with just polynomials, at least locally, and then use those approximations to before transforming back in order to find a way to express the fractional derivative as just in some sense, a limit of classical, well, not classical, but just derivatives, weak derivatives of integer order. So one thing that Bob Strickart's once said to me was that few things have derivatives, but many things have integrals. Even though in calculus it's harder to compute the value of an integral, but it's fairly straightforward to compute the value of the derivative. And so this is one way we can reframe regularity results. So not only are we talking about how to compute derivatives, but whether or not these derivatives exist, we can express this in the language of multiplying by functions in frequency space. So recall that the Sobolev space WKP is the subspace of p integrable functions where all weak derivatives of order 0 to k exist, and they satisfy the integration by parts formula. Satisfying the integration by parts formula is very important here, because just saying that a weak derivative exists almost everywhere leads to some pathologies. For instance, the Cantor step function has derivative 0 almost everywhere, but clearly when you try to apply integration by parts, you get a non-zero answer. So the Cantor function should not be a Sobolev function, even though it is continuous, bounded, and derivatives exist almost everywhere. And it's integrable. And I should also mention the other important aspect is that all derivatives of order 0 to k exist, not just the derivatives of the highest order. So in the main setting we're looking at, we're going to take p is equal to 2, and so we'll say f is in wk2, or just h of k, because h for Hilbert space, p equals 2 allows the Sobolev space to become a Hilbert space. We can say that f is in the Sobolev space wk2, if and only if taking a monomial, multiplying by the Fourier transform of f, and having that be an L2 exists for all monomial degrees from 0 to k. Um, and so since we're starting with a function in L2, the Fourier transforms operation is something that's unambiguously defined. And so the only issue is if we multiply by a monomial in frequency space, we want to be able to transform back, and so we want the product to still be in L2, and that requires decay of sufficiently rapid speed in the frequency side. And so more concisely, a way to frame this is f is an hk if and only if 1 plus c norm squared, that's a polynomial in spite of the absolute value bars, taken to the power of k over 2 multiplied by the Fourier transform if that is still an L2. And what this allows us to do is when you multiply this this polynomial out and expand with the binomial theorem, then this in one fell swoop checks for all the multiplier conditions on the frequency space side and verifies that it's an L2. And so it's not enough just to say c to the power of k times f hat is an L2. You need c to the power of all smaller degrees of k. And so this this framing allows us to express that in one single equation. Otherwise, we only get the weaker homogeneous Sobolev spaces, which are denoted with h dot. But that's a story for another day. Okay, so now that I've spoken a little bit about the Fourier transform and the equivariance, let's go back to the Mobius energy. So since we're looking at simple closed curves, we have functions that are periodic. And so the Fourier transform, they're not just functions, they are series. And series are discrete, and so there's only countably many pieces of data to work with. And so in some sense, that makes it easier and more comprehensible. So the main idea from his paper was to decompose the second variation of the Mobius energy into a quadratic form along with some lower order terms. And the quadratic form, if you just go in directly with the definition of taking the variational derivative with respect to perturbations f and g that are ways in which you can perturb your given curve gamma, you'll get a dominating term of this form, and I'm not going to speak all of it aloud, but you can see for yourself. It's a double integral over that's taken with respect to a principal value of some inner products of the derivatives of f and g, which exist by assumption, along with inner products of their translates, and then we scale appropriately with respect to one of the parameters, and then we integrate. And what's important is that this term that comes out does not depend on the gamma that we started with. So in some sense, this quadratic linearization is universal with among the entire domain of the Mobius energy. The nonlinearity, so where the intrinsic distance comes into account, that shows up in the lower order terms. And so one can show that, at least with respect to the norms, the contribution of the lower order terms to the second variation and on the higher variations is just dominated by the quadratic form Q mentioned above. And so really the great idea with this is that now, instead of worrying about an extremely nonlinear functional that depends on an arbitrary nonlinear simple closed curve, we can just look at this functional that is, at least on paper, more computable in the perturbation directions, and analyze its contributions to changes in the Mobius energy. So there's an important remark to be made here, which I briefly mentioned earlier, which is we need to this quadratic form, because the original Mobius energy is a singular integral, we have to define the variation and the quadratic form associated with the second variation by taking Cauchy principal values and shrinking the domain and truncating our integrand at the singularity, and then sending that the size of that truncation to 0. And normally this can be brushed aside. And it wasn't actually mentioned in He's paper that this guarantees independence of your quadratic form and of the associated variation of the Mobius energy, independently of the truncation limit. Just taking the distance of the parameters, having that being greater than or equal to epsilon, and then sending epsilon to 0. That's kind of a natural way to take a truncation, but it's symmetric in some sense, and so it's not the only way you could take truncations. And in Freedman v. Wang's paper in 1994, they showed that the first variations that are truncated with respect to a curve that is fixed beforehand, that is O of 1 as epsilon goes to 0. So in other words, the lim sup of the difference quotients is finite, but you could still have distinct limits when you take subsequences, and so that, while seeming like it might be somewhat of a pedantic point, it's actually a very important geometric consideration when considering notions of smoothness. And I'll explain what I mean by that in a second. But these ambiguities were resolved when Reiter and Blatt rigorously verified both Fréchet and Guettot differentiability of the energy functionals associated with the Mobius energy, in addition to a larger class of curve energies where instead of having squares in the denominator, we can have arbitrary exponents ranging from, say, 2 to 3. And then we can take the whole integrand and look at the p integrability of that instead of just taking the difference of that. So there's a larger class of integrals, but the Mobius energy case is what I'm going to stick with, because that's that has the nicest mathematical properties. Namely, it has the barrier property that prevents changes of knot types when undergoing gradient descent. So again, why does this point matter? Well, uniqueness of the limits of difference quotients in some ways is the characterization of smoothness. So, for instance, the function f of x equals absolute value of x, that has two distinct tangent lines when you approach from the left and the right. And because you have these two distinct tangent lines, then we can say that absolute value of x is not differentiable at the origin. But you don't want to just wholesale throw away all notions of regularity when talking about absolute value of x, because having one-sided limits, having that exist, having only finitely many different tangent lines, namely 2, that's still an interesting thing to say about our function, and how we can classify this in the broader class of just arbitrary generalized functions. And so the failure of limit uniqueness but explicit dependence in how we take the limit of the difference quotients, and having finitely many ways in which we can have our choice of subsequence arrive at a different notion of a tangent space. This is the main idea behind the approximate tangent spaces of varifolds, at least in the finite dimensional case, which, again, this will take us too far afield, but this is in when looking at functions on finite dimensional Euclidean space. And so by considering the uniqueness of truncations on functionals over the infinite dimensional Hilbert space or Banach spaces that were function spaces that we're looking at, this this is the proper analogy for smoothness in this infinite dimensional case. So in other words, just to summarize, functions are C1 if and only if the graphs are uniquely locally self-similar to a vector space. Of course, you can have self-similarity of the absolute value function when you zoom in at the origin, but it'll be self-similar to a union of two lines, which is not a vector space. Okay, so going back to the resolution. So now that we have this truncation issue resolved, let's just go back to the quadratic form from earlier. So we have that the quadratic form is defined as this integral of the pairwise inner product of the tangents of f and g, along with a scaled inner product of f and g of the differences for f and g. So that's like the second term corresponds to a scaled difference quotient. So given f and g, we can write the Fourier decompositions because it's going from the circle to Rn. So we can say that the Fourier decomposition has this form in just the canonical basis for the Hilbert space of little L2, which is generated by cosines and sines of integer frequency. The information that completely describes f and g are just going to be the coefficients a's, b's, c's, and d's. And so then what we can do is we can express our quadratic form in terms of these coefficients, and that would be enough information to characterize the quadratic form Q. And so the theorem that he showed is that in terms of these Fourier coefficients, we have constants that are uniformly bounded in K, such that the quadratic form from the previous slide is expressed as the infinite series of lambda k, where lambda k is just a series of bounded constants times k to the power of 3 multiplied by just the sums of the inner products of the a's and b's. Remember, the a's and b's are going to be vectors in Rn as opposed to just numbers, so we can take their inner product. And so the important thing here is that the coefficients of the quadratic form with respect to each of the basis components, those coefficients grow cubically with respect to the index. And so to compute these lambda k's, we can evaluate the quadratic form on the standard little L2 basis, EI sine KT, EJ cosine KT. EI and EJ are just arbitrary basis vectors. The i's and the j's don't matter, but the k here does. That's the integer that we're interested in. And if you just go directly into the integral defining Q and just substitute all of that in, you will get a trigonometric integral. And the integral you get, just taking some liberties with the constants involved, we want to get something that depends on k, and so it turns out that a k cubed factor will come out of the integral, and then we get an integral from 0 to k times pi of this trigonometric polynomial. And so this is just so looking at the polynomial contributions, that's going to be a cubic polynomial in k, and so the remaining term, which is a 2 cosine of t over t to the fourth, just after applying an appropriate substitution and then factoring out the universal constants, we get that contribution is the integral from 0 to k times pi of sine of t over t. And that is just bounded because sine of t over t, the integral of that from 0 to infinity is exactly pi over 2, and so that's less than infinity. And so what we're left with is that we have that the coefficients of the Fourier series representation of Q is cubic in the integer indices representing the Fourier coefficients. And so factoring out the cubic, then we just get some constants lambda k that are bounded, that are uniformly bounded in k. So if we apply the Plancherel and the Parseval theorems, and then applying the pseudo-differential characterization of Sobolev space, as I mentioned earlier, the quadratic norm of a perturbation direction f, that's going to just be some expression that is dominated by the 3/4 fractional Laplacian of f, L2 norm squared. And so just translating all of this, what it means is that when the Mobius energy is finite and we are near a critical point, we can say that gamma is in the fractional Sobolev space 3/2, because this 3/2 to the power over 4, you double that because the L2 norm squared, and so on the frequency space side, we're multiplying by something that is O of k cubed over k cubed, taking the square root, so k to the power of 3 over 2. And so that means that all of our functions involved are in this fractional Sobolev space h 3/2. And so with that said, and I haven't really gotten to verifying these details yet, and so this is kind of like where my understanding is kind of at its current limit. It's that after applying a bootstrap argument with the initial condition that you start in h 3/2, this will give us an initial boost to then deduce that near our critical point, the curve is going to be in the Sobolev space of arbitrarily high degree, and so that will give us that will yield that our curve that we started with has derivatives of all higher order, and the initial boost that you need is just that the curvature is cube integral. So the second derivative is in L3, and so that's where the 3/2 comes from. I should also mention that the bootstrapping argument given in He's paper also involves reparametrization of the curve gamma at each step. And so you need to verify, and it's non-trivial to show, but it was ultimately resolved, that all the functionals involved retain their continuity at each step of the bootstrapping process even when you apply a reparameterization of your curve. And in part, one of the implicit things is that we did a normalization of the integrand defining the quadratic form by just assuming that the length was constantly equal to 1. But when you apply the Mobius gradient descent, that could shrink the length. But we can also apply another corresponding slight Euclidean scaling in order to fix the length. Of course, in the most general setting, it would be an infinitesimal Mobius inversion. And you want to show that that has a slight reparameterization of your curve, and you want to show that that still retains continuity with respect to the limits, the truncating limits that define your variational integrals. So in other words, you want to be able to interchange your limits unambiguously. That does take a lot of work to show. But at least right now, I don't know the whole details of it, but at least Blatt and Ryder have claimed that they have successfully resolved that, those details. And so I guess just to finish off, where I think this process could expand is that, as I mentioned, the Mobius energy is invariant under Mobius transformations. But the Fourier transform, that really only looks at invariances with respect to the classical Euclidean similarities, so scalings, rotations, and translations. It doesn't take into account the more general spherical inversion setting. And so I would just be very curious to see that if you start with a Fourier transform theory that takes those expanded set of symmetries into account and then apply these methods, do you perhaps get a stronger regularity result of the Mobius energy? To my knowledge, I'm not sure if Blatt's later paper takes that into account, but they do prove a stronger result, namely that the curves are analytic. So not only do you get like embeddedness into all the Sobolev spaces of the correct order, but you have that the coefficients of the Fourier transform decay at a sufficiently rapid rate to allow for convergence of the Taylor approximation of your curve. And so with that said, that's all I have for today. Thank you again for coming and listening to me talk. I'd love to hear anyone's thoughts or ideas about this, and if someone is out there and they understand this material in a way stronger than I do, I'd love to be able to pick your brain. So my email is liptonm@mit.edu. So once again, thank you all for coming, and thank you to the organizers.
Okay, very good, Max. Thank you. You brought us to consider how to say a quite unusual approach to analyze this integral. So I have immediately a kind of very simple-minded question to you. I wonder if the technique you presented, do you have in mind a way also to tackle all sort of oddities we have on curves in space, for example, cusps, of course, angular points, but also other type of singular points that may arise as the curve evolves in space?
Yeah. So So going back to the original definition of the Mobius energy integral, one can actually show that if you take a curve with a cusp in it, that is, you have two tangent lines that go at a that hit each other at a prescribed angle. When you look at the contribution of the Mobius energy of just those two line segments, and you just go and try to compute the Mobius energy of just like a basic curve, like with that property. So like computing the Mobius energy of two straight line segments that intersect, you'll get that the integral diverges, essentially because of that lack of uniqueness of the integral from the left hand and the right hand side. And so what that means is that in order for the Mobius energy to be finite to begin with, you need to have you can't have that sort of kink occur like in your curve. And how I believe that would manifest when looking at the Fourier series representation of said curve, well, you would the associated integrals wouldn't be like absolutely convergent in and of themselves. So you'd have to like take some limiting process that approximates your kink by smooth functions of some sort. And I think with that you would get that the coefficients would blow up on the Fourier series frequency side. And so that would preclude convergence of any of the infinite series that we started with. And so you would get so a lot of the formal symbolic manipulations that one would try to do in order to look at the regularity of the critical points would not be I guess well posed, because you'd be doing you'd be like manipulating divergent series.
Sure.
But
Sure.
I think it would be interesting to see that in action by directly looking at like an explicit like that's the behavior that I expect to happen, but to my knowledge, no one has actually like done that computation to verify that the Fourier coefficients blow up. But that's what should happen, and it wouldn't be surprising, and that's how the Fourier method would fail for kinked curves.
Thank you. Questions from the audience, please. Okay, since none. So thank you again, Max. Thank you, and bye-bye.
Yeah, thank you so much for showing up, and hopefully I'll see all of you soon.